Hey, good afternoon. I apologize that I'm not there in person, but I'm at a conference in Long Island, New York, and we're here on Long Island. We're at Brookhaven Lab down the street. They're building the electron ion collider. They have a facility with a ring about uh, 3 miles around that has collides nuclei together, and they're going to enhance that to add an electron ring to that so they can do electron on nuclei. And since electrons are effectively, as far as we know, point-like particles, that gives us a very precise way of studying the nuclear interaction. So that's what I'm doing this week, but I will be back next week. And my apologies. Hope things go well. So let me start by, I want to go over the key for the quiz today. And again, the quizzes are always 2 out of 3. So if hopefully that goes well. If you get 2 out of 3, that's 100%. I'll grade these and pass these back. I apologize, it won't be till next week, but hopefully everyone did well. So just to get started, question number 1, for transverse wave, the displacement is perpendicular to the motion of the wave. And perpendicular, we'll take any word along that line, doesn't have to be my wording, but the point is when I was wiggling that long spring back and forth, the wave was moving back and forth left to right, but the motion of the spring was up and down perpendicular to the motion of the wave. So a light wave is transverse, a water wave is transverse, but a sound wave is not. A sound wave is a longitudinal wave. And for a longitudinal wave, the motion is along or parallel to the direction. And so for this with the slinky, I illustrated both of those. The slinky, when I went left and right, that was a transverse wave, but then I went back and forth, and you had the slinky would bunch up and stretch out, and that's a compressional wave. That's a longitudinal wave, and that's what sound is. So when a speaker goes back and forth and makes sound, what it's doing is it's compressing and the air molecules, and it's sending those compressions to your ear, and that's what you hear. A violin string, when you bow a violin string that goes up and down, that motion is transverse to the direction of the uh, wave along the string. But the effect of that violin string going up and down, it makes the wood of the instrument go back and forth, and that generates compression and refractions, which we interpret as sound waves. So just wanted to clarify that, and hopefully that went okay. Next one, question 2 and 3 was combined. So here we have an open organ pipe illustrated here. And again, this, you'll see this over and over again. We don't expect, heavy duty math in this class, but the open and closed pipes, you'll see those over and over again because that's the model we'll use for the instruments, the musical instruments. So do get familiar with this. If you had any trouble in the quiz, do get it fixed because again, you'll see this on the exam, and this is the model we use. So it's an open organ pipe. It's open at this end, it's open at that end. And so, this represents the pressure wave. It's at atmospheric pressure here, atmospheric pressure there. And then this is the lowest frequency or longest wavelength that will fit in there. Okay, and the key step to all these is figuring out how many wavelengths fits in the pipe. And although it may look like a full wavelength, let me draw it out. Here's a half a wavelength, and then if I keep going, the other half. Let me try it again a little bit neater. All right, it goes up, that's half a wavelength. There's the rest of the half wavelength. And so you would actually, only half a wavelength fits in the pipe. And what that means is the wavelength is twice the length of this pipe. Okay, so that's the first step. In this case, 3 meters. As Professor Baker will tell you, we usually measure organ pipe in feet. 3 meters, that's, a meter is about a yard, so that's about 9 feet, 10 feet, something like that. That's a fairly long organ pipe. And so that's going to be fairly low in frequency. So let's work it out. So here's the I'm going to take 340 for my velocity. You'll see I take different numbers. I took 350 before. We'll talk about that a little bit later, but let's use 340 for this example. And then this is the key equation. It relates the velocity of the wave to frequency and wavelength. Again, we're going to be using this over and over again, so make sure you're familiar with it. So I can get frequency if I divide by lambda, and so the frequency is the velocity divided by the wavelength. So here it is, this is the frequency, and I just figured out that the wavelength is twice the length of the pipe. So the velocity is 340, the length of the pipe is 3 meters, and I figured out the full wavelength is twice that, 6 meters, and I get about 56 hertz, which is a fairly low note. The audible range is from 20 hertz, about 20,000 hertz, so this is getting down there in the bass. That's a fairly low note, but a 10-foot pipe is a fairly long one. So hopefully that went well, and I will pass that back and to you next week. And again, be glad to take any questions on that. Okay, next, let me go. I want to take a quick look at the lab that we went over, and just to remind you how to get to that. Let me see if I have a. Here we go. From our class page here, if you go to the labs and pre-labs, you'll find all the materials down here. Okay, in particular, on Thursday, I will go over pre-lab 2, so you might want to take a peek at that in advance. But here's lab 1. And again, the TAs, gave you the overview. We appreciate having those 3 TAs and the lead grad student, especially since some of the TAs have taken the course before. That's a real benefit because they have both the physics and music experience. So here are the objectives, and hopefully you were able to write that into a couple sentences to make an abstract. But the point of this was to have you do a few measurements, and some things are harder to measure than others. If you look in the cartoons or comics, often they portray scientists as being, interested in, all sorts of crazy precision. So they want to know the, length of their desk or their pencil to 15 digits. And that's actually not so accurate. We're less interested in the precision and more often in the relations. That's why when we did the dimensional analysis we sort of figured out the formula for a pendulum or a mass and a spring, and we found out that it depends on these things, but not those things. Those relations are more interesting. But it's also important to know what the limits of our measurements are, and that's what we're going to be exploring here. So let me skip down to where we did it. The first thing we had you do is measure the rod length. And so here in the rod, we gave you a 6-inch ruler first and a 12-inch ruler. And with the 6-inch ruler, we gave you something that was more than 6 inches long, so you actually had to do this in pieces. So that's one possible source of error. But the other is a little bit more subtle because those 6-inch rulers, if you look on them, I think they were labeled as scientific research, or SR, the initials. That's a shorthand for us. It stands for short ruler. And so we had those specially made. They're 4% shorter than a normal ruler. And so what that means is that when you measure it with this and measure it with this, you're going to get a different number by about 4%. That's called a systematic error. That's what happens when your equipment isn't calibrated, or it's not, or you think it's calibrated, but it may be miscalibrated due to some effect you're not aware of. So that was a way that we could introduce systematic error to you. So hopefully by making 5 measurements, your accuracy was enough to see that difference. Okay. So not to trick you, but that's why we did it. That's also why we had you do the 6-inch ruler first and then traded you for the 12-inch ruler, because we locked those up and back. We don't want those to get out in the wild and spoil all sorts of other scientific measurements, but it's a interesting teaching tool. The next thing we did was the circle diameter, and the challenge here was those circles we made were imperfect. So they weren't quite round, and that means if you measure the circle this way, versus this way, you could get different numbers. And also, if you don't quite get the diameter, you're going to be off a little bit. So again, that's a very, standard type of uncertainty, and there are a number of sources for those errors. The next one was the candle flame. And this is something it's just poorly defined. Where do you start? What's the bottom of the flame? What's the top? It's wiggling, it fluctuates. You can't get really close or you'll burn yourself. So it's a poorly defined, quantity, but sometimes you encounter those types of things and you have to do the best you can or define it or somehow stabilize it. So this, we expected you have quite a bit of variation, but that's just the nature of it's sort of a difficult to define object. Finally, the reaction time. Hopefully, you did it so only one person did it, because if you switch people in the middle, you may have different reaction times. I'm a little bit older, so my reaction time may be slower, but there are all sorts of possible variations. Did you see your partner twitch before they let go of the ruler? Did it accidentally touch your hand and trigger you? Other things, did you get lucky? Things like that will do it. And I think the reaction time, the ideal reaction time is something in the order of half to 3/4 of a second. That's just the amount of time it takes for when you see something to send the signal down the neurons to your arm to contract the muscles. And it's really quite remarkable that when you think about the speed of those signals, those are actually quite fast. Finally, the mass of a cold material. Here we made you measure this over 5 minutes. And the challenge here is that the liquid nitrogen was boiling off. So as a function of time, the mass was going down, and you got numbers that kept going down, down, down. So you can average it and all that, but then you've got a systematic error because you're trying to measure a moving target. So anyway, and then at the end, hopefully you wrote up a succinct set of conclusions. But the point was just to introduce you to some of the difficulties we have when making measurements and make you aware of what comes into that, both in terms of systematic errors and random errors. And actually, the intro piece here. Let me pull up the pre-lab. Had some very nice, this diagram I like quite a bit because it summarizes it quite succinctly. The difference between precision and accuracy. So in this case, if I look at this group, I've measured very precisely. All my measurements are very close together, but it's not accurate. And so, for example, that could happen if my ruler is miscalibrated, like those short rulers we gave you. Over here, this is not accurate, but the average of those measurements will be very close to the correct number. Okay, so that's important there. And these are things we want to be aware of. Over here, this would be characteristic of a systematic error where you have a short ruler. This would be characteristic of something that's hard to measure, like your candle flame. So I thought that did a very nice job of that. Okay, so next, what I would like to do is go on and talk briefly about some of the things that from chapter 3, and Professor Baker can expound on these. But I'll show you some demonstrations that I find are quite useful. And to show you where I start from, if you go to this link to general resources, there's lots and lots of stuff here. Lots and lots of stuff here. But the Colorado, right here, let me get the crayon out. Colorado has a bunch of very useful simulations. I'm going to use a few of these to just illustrate some of the properties of waves. And let me pull this up. And they have a number of demonstrations, but I'll use this. So for waves, water waves, sound waves, light waves, to illustrate the property of waves. In this case, we'll use light waves. Sound waves actually do the same thing, but it's easier to see with light waves. And basically, I want to tell you about four things: reflection, refraction, interference, and diffraction. And we'll go over these again, but I'll just step through these rather briefly. So reflection, um, so let me turn this on. So this is a flashlight. I can wiggle the flashlight. And for example, here I have a air-water interface. Um, I have an air-water interface. And when the light comes in, some of it is reflected. Okay, some of it is reflected. And if you were to measure the angle, for example, this angle is exactly equal to this angle, or equivalently, this angle is the same as this angle. So the angle of incidence is equal to the angle of reflection. So this would be, for example, if you just come in and you have a mirror, it just comes in and goes out. Okay. But then if you have an interface like this, in this case, I have air and water, when the light enters the water, it actually bends a little bit. And that let me switch from um, the ray model to the wave model. And let me put it in like this. And what you see is as these light rays are coming in, when the light rays enter the water, because the water is denser, the light rays slow down. And let me just pause this for a sec. Okay. And the light rays slow down. And what you see here is that, you know, these light rays in air are moving faster than these light rays here. And these light rays aren't keeping up, so that's why it bends like this. These light rays up top are moving fast. The light rays down here are not moving fast, and that's what causes it to bend. Okay. Um, all right. So that's essentially refraction. And it simply comes about because of the different wave speed in the different materials. And I think I can do this. Let me switch it back the other way. Let me do, glass here and air here. Uh, yeah. And now, uh, and now you see, instead of bending away, it's actually bending less when I go the other way. So that's simply you know, that's simply a matter of the wave speed. And so when you go into different materials, if the wave speed is different, it will cause the light to bend. And either if it's slowing down, it'll bend away from the direction like this, or let me see if can I do it? No, it won't let me go. Won't let me go into the water. Yeah. One other interesting thing that comes up, let me go back to the case. I'll do, I'll do glass air, switch it around again. All right. So here, um, when I'm going from glass into air, you see instead of bending down, it's actually bending up because I've switched things around and it's moving faster. This is moving faster. So if I scribble the wavefront's moving faster, I'll try it again. It's moving slower up here and it's moving faster down there. So this end's not keeping up, it bends away. But something very interesting happens here. As I go further and further and further, at some point, the light ray does not escape the glass. The glass is on top up here and the air is on the bottom. At some point, it does not escape the glass. And that turns out to be quite useful because this is how you make a fiber optic. A fiber optic is typically made of glass, and it's glass with air around it or some coating. But because of this property, you have complete internal reflection and none of the light is lost. And what that means is if I take a laser beam and send it down a thin piece of glass, it will bounce back and forth inside the glass, but none of it will escape. And that means I can send that laser beam down miles and miles and miles, and that's how your internet communication is done. It's actually fiber optics with a different color laser beams to multiplex it. So that's a key property. So for sound, reflections are quite evident. We have echoes all the time, but refraction is a little bit more complex. It's a little bit more uncommon to do that. Probably the only example I can think of is where you have differential temperatures like water above, air above a lake or something, where the, air next to the lake is cool or hot, and the air up high is a different temperature. So reflection happens quite a bit, but refraction not so much. So those are the first two, reflection or refraction. Reflection is just like reflection from a mirror. Refraction happens when it goes to a different medium, the speed of the wave changes, and that causes it to bend. Okay. And um, let me do a couple more examples. This is another demo they have, and this is sort of a cute one. Um, okay. So here I have a block. If I shoot it straight through, it goes straight through, but something sort of interesting. Let me try to simplify this, that out of the way. Okay. And um, in this block, you notice, it comes into the block, it bends, it leaves the block, it bends the other way, exactly opposite. And in fact, if this is a square block and the faces are parallel, you see the outgoing light ray is in the same direction as the incoming light ray. It's just shifted over a little bit. Okay. And it's just shifted over a little bit. And the same works if I go this way. Okay. So, that works very nicely. So if I have a, just plate glass window, if I have a plate glass window, if I look at an object through that, it may be shifted up and down a little bit, but it's not distorted. So let's distort it a little bit. The first thing I'll distort it with is I'll distort it with this. Okay. And notice as I, put this a little closer. Okay. Notice as I bend this back and forth, as I bend this back and forth, it tends to bend the light. Oops. Uh, there we go. Yeah, that's better. Yeah, as I bend this back and forth, it tends to bend the light back toward the center. Okay, so if I misalign this, it bends it back toward the center. If I misalign it back, bends it back toward the center. So this is a converging type lens, and it simply has to do with the thickness of the lens and the way it bends the light. And so, for example, if you wear glasses, you might have glasses that do something like this. And what it does is it helps focus the light. And if you look closely, there's some point way out here on the other side where, oops, come on. There's some light way out here on the other side where this is focusing on. So this is a converging, here on my crayon, there we go. That's a converging type of lens. Let me contrast that with this one that's thinner in the middle, okay? And so here, this is a diverging type of lens. You see it's bending it away from the center line, okay? And then of course I can put them together. I put them together, it's the same as the plain block. Let me do one other example. This is the prism, okay, and that's rather interesting how it bends the light. And let me send in a ray of light, okay. So I go back to here, but let me change the color. Let me change the color, okay, and let me try to exaggerate this. All right. As I change the color back and forth, what I want you to notice is that down here, the bending changes. Okay, so if you look at where this intersects this panel down here, as I move it back and forth, gotta make my crayon go away. Come on. There we go. As I move it back and forth, it's rather slight, but it does move a little bit. And that's because different wavelengths of light bend different amounts. And so when you send it through a prism, what it can do is it can, those different colors will bend different amounts. And so a prism will sort of spread out the colors. And that's why you get the that color type effect going on there. It's rather subtle, but you can see it in something like this. So, okay. All right, enough of that. Let me minimize that. The That's reflection and refraction. The next thing, next two I want to do, and again, these are the uh, Colorado demonstrations. The next thing I want to do are just simple interference and diffraction. Interference is when you have two wave sources. So, for example, right here, I have water dripping. Let me reload this. Okay. So I have water dripping. Okay. And it just goes out in a circular pattern. Okay. But now, if I have two sources, okay, if I have two sources going out, all right, the waves will add up. In some places, they'll add up to be if I have a crest and a crest, that'll give me a big crest. In some places, I'll have a trough and a trough, and that will give me a low point. And so the two waves will add up and interfere with each other. And this is a type of pattern you get. And I can up the frequency and decrease the separation, and I get various patterns. Um, Let me pause that and let's go to the sound wave one. Sorry, let me reload this. And I don't you may or may not be able to hear this. You may or may not be able to hear this, but uh, if you pull this up in your own, you can actually move the person and you'll hear different things. And you see their lines along which there's no sound at all. And if you get to one of those nodal lines, um, so I don't know if that was audible over the Zoom, if it was set to pick it up or not. But if you slide up and down, you can go over nodal lines and you'll pick up either the large sound or the small sound. So with interference, if you have two sources, that's what gives you interference. Okay. Um, and so this is a typical interference pattern. The the characteristics that generate the interference, you need two things for the interference. There are two length scales involved. And basically, you have the wavelength, that is the wavelength between the wavelength of the sound waves, it's something like this, and you have the distance between these two. And so if those are comparable distances, then you'll get an interference pattern. Um, I don't want to take up too much time, but the last one I want to talk about is the diffraction. Well, actually, let me do, um, let's see, wave interference. Let me do the, yeah. Um, and let me do two slits. Okay. I'll actually start with no barrier. So here's a wave pattern. Actually, you'll be doing this down in the lab with the wave tank. Okay, um, like that thing. All right. So so if I have a series of waves coming in, they look like that. Now let me put up a two slit barrier. Okay, and I'll move this back a little bit. Okay, and basically, each slit is looking like a source, and that's it's looking like a source, and then they're interfering, and you're getting dark and light spots on the other side, from uh, from that pattern. If I make it a little bit smaller, let's see, if I make it a little bit smaller, you can see it, I think a little bit better. Let me go to one slit. Okay. And with one slit, what's rather interesting here is um, the waves don't just go straight through. In fact, if I have a small opening, in this case, I have a rather small opening here, that looks like a point source, and the waves spread out in all directions. Okay. And so that means, in terms of sound waves, what that means is sound waves can bend around corners. So if you're sitting in a classroom down the hall and the front door is open, the sound waves can actually come in the front door and kind of go around corners and get to you because of this diffraction phenomenon. And the diffraction phenomenon, again, it depends on the relationship between two lengths. You have the wavelength of the sound, which is the distance between these here, and you have the size of the aperture. Okay. So, for example, let's think about, let's pretend I have sunlight coming through a window. I have sunlight coming through a window, and the window is maybe 3 feet wide, and the wavelength of, sorry, not sound, light coming through a window. Um, the window is 3 feet wide, and the light is 5,000 angstroms. Those are so different that the light doesn't diffract at all. If you want light to diffract, you have to make the slit comparable to the wavelength of light. And if the size of the slit and the wavelength is similar, then you'll get diffraction. But with sound, as we learned, A440, that's about a yard. And so that can diffract through a window, it can diffract through a doorway or a column or something like that, and then you do get diffraction. So let me pause there, and we'll come back to these things again. Um, just very briefly, for the quiz, uh, just so you know what to expect. Uh, on the quiz, I'll do a little bit more of the organ pipe. Uh, I'll have you do a organ pipe, maybe with a higher harmonic, and then I'll also have you do a closed organ pipe. So make sure you're familiar with that, so you've got that down. Hope that goes well. Again, I will see you shortly, and yeah, and have a good afternoon. Thank you.